Can I have a, like, it's right there. Right here.
All right. Everybody had a nice break. Yeah, I'd originally put up some learning exercises, and I never published them. But then ultimately decided that didn't really need to get through that stuff anyway. So what our material end, if you're following along on the GChem website, let's see, it'll just go, it'll be, I guess it'll be a little bit limited in terms of content. It'll just be through Voltaic and electrolytic cells. So just the learning exercises we've done up to now. So that's like 12.1 and 12.2. And then we'll cover up any of this remaining material. We'll skip over batteries and additional content, but there's some stuff in the potential and free energy section in particular that I want to get to. We'll cover that in our last day or two of classes. So an exam on Wednesday, and it'll just be over sections 12.1 and 12.2. So balancing redox reactions, and then some of these basics on electrochemical cells. And then we'll finish up today, voltaic and electrolytic cells. We could do a little bit of, no, we'll probably stop there. That's a pretty clean place to stop. Yeah, so we'll finish up with voltaic and electrolytic cells. And then anything that we don't cover on this, we'll just have on the final exam, which is whatever its normal time and such that's on the syllabus. So, okay, so yeah, let's see. Well, this is apt because this is what we're going to talk about today. So voltaic is another word for galvanic or whatever you think of when you think of a battery. You know, it's a battery that has a charge on it that you can use to do work. Electrolytic is we're going to talk about those in more detail. So I think we finished up talking about these electrolytic cells over here. I'm sorry, not electrolytic, so the standard potentials. So this table, which of course you don't have to memorize, this is something you're always given, is a list of standard reduction potentials. Reduction and oxidation are kind of like acid and base chemistry. They're sort of opposite sides of the same thing. You can't have an oxidation without a reduction, just as you can't have an acid without a base. You sort of need both of those there. And so you could just as easily have written these as standard oxidation potentials. And if you did, everything would just be flipped over. So let me write it so it's not confusing. So these are our standard reduction potentials over here. This is, I think, more typical of how you see these written. But you could also write out a table of standard oxidation potentials if you wanted to. And the potential energy associated with that is just the exact same, but just with an opposite sign on it. So now you see I want to write out this reaction for oxidizing fluoride instead of reducing fluorine. So it's an oxidation. I know it's an oxidation because electrons are on the right side. So if my electrons are on the right-hand side, that means I'm losing electrons, so it's an oxidation. If I look over here, they're on the left-hand side. So they're gaining electrons, so they're reduction. So if you think of the electrons as products or reactants, that can kind of cue you in as to whether or not it's an oxidation or a reactant. Naturally, they're not actually reactants or products, but it's okay to think of them that way. So electrons are kind of in the product of an oxidation. But yeah, what's our standard potential associated with this? all we do is we flip the sign on the voltage. So now it's negative 2.87 volts. And then if you want to kind of get the overall voltage for a cell, we have these different equations that we can use. So for example, let's use this one. For example, if we're looking at, this is an example from the GChem website, but if we're looking at a battery that looks something like this, this is just to hopefully jogging your memory, since I know we just had a break. But let's say we're looking at something like this. So at the anode, we have solid nickel. And then over at the cathode, we have this solution of iron 3 that's getting, what is that, reduced to iron 2. And we have, of course, a platinum electrode over there because these are both cations. So remember, if you have charges on these, they're not going to be anodes or cathodes. They're going to be in solution. And so we have to use platinum, which is inert. If we wanted to know what the cell was, what the voltage was in that cell, you would say there's a couple of equations you could use, but the E cell under standard conditions, that's what the little knot means, is equal to E reduction plus E oxidation. And so this equation's nice. I like this one. The other one you can use is E cathode minus E anode. But I like this one because it sort of gets at what we're talking about up here, which is just that sort of the total, I don't know, the total potential on the cell, or the total voltage on the cell. You take the reduction half reaction and the voltage associated with that, and then you take the oxidation half reaction, which here would be iron 3 going to iron 2, and the voltage associated with that, and you add them together. So what we're looking at here is we're saying, okay, nickel, if it's being reduced, of course, not my table, the nickel plus 2 electrons. How do I have this backwards? And ox, oops. Yeah, nickel is not being reduced, but oxidized. It's going to lose 2 electrons. That's going to be the oxidation reaction. And then on the other side, so we'll have to look that up in a table. And on the other side, we'll have the reduction reaction. And that's going to have its own voltage associated with it. Let's see. So this one, actually, I must be in here. Good. Yeah, so this oxidation has a potential associated with it of negative 0.25 volts. And then the reduction has a potential of plus 0.77 volts. And so E cell is just the addition of these. Yeah, sorry. I'm looking at cathode versus anode. Give me 1 second. It's plus an electron. This one is correct. Yeah. Sorry, so if you look up, let me move this, clean this up a little bit. So if you go in their table, and look up the potential associated with this. You'll actually find the reduction potential. That's sort of the lesson. I messed up myself. So you look up the reduction potential. This is the reduction potential, though, and we're actually, the nickel here is not where the reduction is taking place, but where the oxidation is taking place. And so in order to get the oxidation potential here, when you flip the reaction, you just flip the sign on the voltage over here. So the negative 0.25 goes to plus 2.5. And so you can add these and get 1.02 volts. If you look at the other way to do it is, you don't have to worry about doing kind of the sign flip. So here, right, I flip the reaction around. So I look up the reaction. It's written as a standard reduction potential typically. So I flip it around and then flip the sign. And then I just recognize that all I'm doing is adding up all the different potentials for the cell. And so I end up with 1.02 volts, which is the mistake I made. I left the negative there. But if you don't want to worry about that, what you can do is you can just write out E cell is equal to E cathode minus E anode. And so here, our cathode is here, with the iron 3 is going to iron 2, where our reduction is taking place. And so we write out the reduction potential. So this one is written just strictly in the reduction potentials. And so that would be 0.77, and then minus the reduction potential at the anode, which is negative 0.25. And so the only difference between these two equations is that this one, in this second equation here, the sign change is taken care of. It's taken care of for you. So this is written in terms of the reduction potentials already. And then it's just this negative sign kind of takes care of the fact that at the anode, you're going to flip the sign on. You're going to flip the sign because you're actually not using the oxidation potential. I mean, sorry, you're not actually using the reduction potential, using the oxidation potential. So they both work as long as you're just kind of careful about what you're writing out. But it doesn't matter which one you use. One thing to note. Yeah, so I'm maybe not explaining this very well. So when you're adding these things together, what you're really using, if you remember back in like when we did thermochemistry, we're gonna put this maybe just over here. When we did thermochemistry, we do this thing where you could take like delta H and add them up. It's called Hess's law. This is kind of the same idea. Like I'm taking these two equations here and I'm adding them up. But the way that things are tabulated, they're just tabulated such that they're always in terms of the reduction potential. So if I flip this around, so you'll notice here, the nickel and the 2 electrons are on the left-hand side, so it's a reduction. But when I flip them to the other side, now the 2 electrons are on the product side. So just flip that reaction around. I just need to make sure that I change the sign here. That's all that's going on there. So this is really what you're doing, is you're kind of adding these things up just in the same way that you would add delta H or something up. And so you get a sign change there. But because, unlike with Hess's law, where you'll have like 8 reactions, here you're generally only dealing with 2 reactions, an oxidation and a reduction. You can simplify this a little bit. Instead of kind of worrying about doing the sign switch yourself, you could just write out this equation where you just subtract the anode reduction potential from the cathode reduction potential. And so this is the oxidation potential. These are both reduction potentials. That's the difference between these two equations. Let's see. Yeah, so one thing to note on this is that, so this, the way I've written this out, it's not actually balanced. If you look down here, so up at the top, I've got 2 electrons, and down here I have 1 electron. If I wanted to balance this thing out, I could just multiply the bottom reaction by 2. This is something that is not the same as the thermochemistry stuff. So in thermochemistry, if we multiplied, remember, if we multiplied the bottom by 2, actually, I'll just rewrite the whole thing. So let's say I want to balance this out. This one's pretty easy to balance, unlike some. Take the top, now we're going to multiply the bottom by 2. Yeah, when the chemical equations don't have any oxygens or hydrogens or anything appearing in them, typically they're pretty straightforward to balance. You'll notice I just had to multiply this bottom thing by 2. Okay, what happens to this though? The oxidation potential, obviously, for the top one doesn't change at all. But also the bottom doesn't either. So when you change this, it doesn't actually change the reduction potential at all. That potential difference is the same regardless of the number of electrons that are involved in the transfer process. So just be careful that you don't kind of overgeneralize sort of what I was talking about what we did in thermodynamics. We're not actually going to take and change this. This is not 0.77 volts per moles. This is just the 0.77 volts. That's the reduction potential relative to whatever the standard hydrogen electrode is. It's not dependent on the number of electrons transferred. It's just the potential difference between those 2 states. But practically speaking, we don't multiply. So say like E reduction or oxidation, whatever. Is the same regardless. I don't know how to say that exactly. It's the same regardless of the So it doesn't matter if I balance the equation or not. This stuff is still the same. That's the main takeaway here. Let's see. Okay, so I think that's good. So yeah, so generally speaking, the way that these problems work, I'm trying to think of like the multiple different ways that we can ask this. You're generally just given, might be given something like this, where you're given a cell and you're asked to, or a drawing or something, but you're given some sort of setup for a battery, an electrochemical cell. And then you're asked to calculate the voltage associated with it. So for this exam, we're just going to look at standard potentials, which is what this little knot means. We should have time on Friday or Monday or whatever to cover the non-standard ones. That's when things are not under standard state. So we haven't really talked a lot of detail about that, but don't worry about it too much right now. But in order to do that, you just go and look it up at the table and you just make sure that you're consistent, either adding the reduction and oxidation potentials or subtracting the anode from the cathode, where you're using both reduction potentials. Yeah, I think that pretty much covers that. Okay, so let's look at voltaic and electrolytic cells. Okay, so in this example that we looked at up here, we had nickel at the anode. And then we had a platinum electrode for the cathode. And the nickel is being oxidized to nickel 2. So oxidation is recurring. And then at the cathode, we had this reduction occurring where we're reducing iron 3 to iron 2. So if we took this, cell, we can plug in a voltmeter to this thing. So in a anode, we would label with a negative charge and a positive charge for the cathode. And so electrons in this cell are going to flow in this direction. They're going to flow from the anode to the cathode. It's like the nickel 0 here is going to give up electrons and kind of go into solution as nickel 2. And then those electrons are going to get driven over here to this cathode where they're picked up by iron 3 and reduce the iron 3 to iron 2. And so you can kind of think of it as like the positive terminal is where the electrons are being attracted to, and the negative ones are kind of pushing the electrons away from it, is one way to kind of think about the flow of electrons here. So it's like the electrons kind of move towards the positive charge. If we were to hook up a voltmeter here, the voltmeter is going to have a positive and a negative terminal as well. And a voltmeter will allow us to measure what the potential is for that cell, which we've calculated already. Is 1.02 volts. Yeah, so this type of cell we'll call this a galvanic cell. You'll also see it called a voltaic cell. And then sometimes you'll also just see it written as electrochemical cell. But in all of these cases, these are all just descriptions of the same thing, and they're all unified by the fact that the electrons spontaneously flow from the anode to the cathode, and you'll measure a positive voltage. Oops, I got my charges flipped there. You want to hook the negative terminal up over here and the positive up there. But yeah, if you hook up a voltmeter there and you match the terminals up properly, what you'll see is 1.02 volts on the readout there. Let's see, if you were to take, however, I'm trying to think of how you like it. Yes, it's sort of, oh, I'm missing my salt bridge here. Whatever's in here, like a potassium nitrate or something. Yeah, so this is a galvanic or voltaic, etc. The salt bridge is there to balance charges. I think we talked about that in the, I don't know, some point in the lecture, but as you, for example, over here, as you get more nickel, so as the electrons flow out of this solid nickel, you generate nickel plus 2 in solution. And so you're building up positive charge in the solution. And so if you had no salt bridge, you would just keep building up positive charge in that solution. And so what the salt bridge does is for every nickel 2 that kind of goes in a solution, 2 nitrates will kind of come out of the salt bridge and dissolve in here. So it's just to keep charge balance. Same thing over here, like as the iron, so charge is conserved, I guess, is the way, maybe one way to say it. As iron 3 goes to iron 2, I'm losing a positive charge over here. And so every positive charge I lose, some potassium comes in a solution. So they're spectator ions in the sense that they don't undergo any kind of chemical reaction, but they are involved in the kind of keeping the charge balance. If you didn't have the salt bridge there, you would build up a bunch of positive charge over here, and I guess negative charge over here because there's some counter anion in solution, and then your cell would just stop working. So the salt bridge kind of, it pretty much just completes the circuit, I guess is the way to think about it. If you didn't have that there, then you wouldn't be able to complete that circuit. All right, so in an electrolytic cell, so these are all, this is kind of mostly what we've been talking about. If we look at, so yeah, let me write a quick definition down for these. So these are like cells where there's spontaneous flow of electrons from the anode to the cathode. So this just happens spontaneously. I hook this thing up and this reaction just goes and it moves electrons from here to here. And that just happens because, you know, it's kind of like throwing a ball up in the air. You know, the ball is going to come back down to the ground. In an electrolytic cell, this is when you have something that's not spontaneous. So like an external, or how'd you say this? Say like work is done on the cell to drive a non-spontaneous so here, this happens naturally. Electrons go this way. If we wanted to, we could drive this to go in the opposite direction, and then it would become an electrolytic cell. So you're basically, you're kind of moving the, you're kind of pushing the ball uphill in a sense. So in this case, it's sort of like, you know, if I want to imagine some simple physics diagram, a lot of times people use pressure in pipes, I guess. I always end up using these gravitational ones. But if you have a ball and you've got a hill, right? This is, I'm just like, put the ball at the top of the hill, it naturally is going to roll to the bottom of the hill. That's what we're looking at here. So electrons just sort of naturally flow this way. In an electrolytic cell, you have the opposite situation. If I just put the ball at the bottom of the hill and leave it there, it's not going to spontaneously go up the hill, right? We have to do something to kind of move it up. So somebody has to get here and push it up the hill. So And so that's really the difference between an electrolytic cell and a galvanic cell. Okay. In terms of conventions, it gets a little bit more confusing for these. So you still write out the you still write it out as the anode and the cathode. The anode's on the left-hand side and the cathode's on the right-hand side. That's always true. But you label the terminals differently. Oops. So up here, you'll notice that we take our cathode. The cathode is labeled positive because electrons are flowing from the anode to the cathode. When we come down here, though, now the cathode is labeled negative. Yeah. So if we hook up, this gets a little bit confusing. There's a question in the slide deck that's really confusing around this that I don't really want to get super into. But the key difference here is that you're going to let's use the example from up here at the top. So let's say that for let's look at this. So if we have originally we're looking at this as a battery. So we know that the E cell for this is equal to 1.202 volts. What if we flip this battery around though, and we wanted to run it in this direction? So we take platinum, and so we run it this way. Now E cell, because we flipped everything, all the signs flip around. Now E cell is equal to negative 1.02 volts. And so this reaction is not going to spontaneously flow in this direction. So everything is the same now, but we just kind of, I don't know, relabeled it all. We're trying to go uphill. So sort of the natural state of things is naturally what wants to happen here is when I hook these two electrodes up and I connect them with a salt bridge or whatever, the nickel wants to be oxidized to nickel plus 2, and the iron is going to be reduced to iron 2. Iron 3 is going to be reduced to iron 2. What I'm trying to do down here is I'm trying to go in the opposite direction. I'm trying to take iron 2, I'm trying to oxidize it to iron 3. I'm trying to take the nickel and I'm trying to reduce it down to nickel 0. So essentially I'm trying to do the opposite reaction. And so what I want is for electrons to flow in that direction. but that's not what happens, right? If I hook this up, electrons are actually going to flow in the opposite direction, because that's what we've seen up here. So essentially, all I've done, this is where things get a little bit confusing with these. So up here in the galvanic cell, right, I've written this out as an anode and a cathode, and I've hooked this wire up to allow electrons to flow. Now I've just said, okay, well, screw that. I don't want this to be the reaction. I don't want the electrons to flow from the nickel to this platinum electrode over here. I want to do the opposite thing. I want to have the platinum electrode on the left and have that be the anode, and I want the electrons to flow towards a nickel cathode. So if I just hook these things up, though, that's not how this cell is going to work, right? Electrons are going to flow back in this direction. I haven't really done anything other than switch these flasks around. And the chemical battery itself has no knowledge of that. Just because I'm calling this an anode doesn't magically make it an anode. So you would still measure a voltage. You would still measure a voltage on this, but it would be kind of going in the wrong direction. If we want the reaction to go in the direction as we've written it, which is like this, oops. We have to drive that reaction. So we're going to have to apply an external source of power, an external voltage to this to get it to go. So I could hook up a battery here. Let's see. I can just draw the thing with the battery. I forget which side is which in this, but I'll just put a positive over here. About like this. There we go. It's my chemist battery. So I've got a battery that I've hooked up here. And I can apply a voltage. If I apply a voltage that's greater than 1.02 volts, I can start to drive the current to go in the opposite direction here. And so I drive the electrons to go in the opposite direction. So you can think of this battery that I've attached here as just sort of giving a little bit of a boost to these electrons. The electrons are kind of stuck at the bottom of the hill here. And I take the battery here, and the positive charge, you can imagine it as the positive charge on the battery here will sort of attract these electrons up. So they're sort of pulling the electrons towards the battery and then pushing the electrons on the other side. So here's a negative charge. So when they come out on the other side, I've got an electron there. It's sort of pushing them onto the cathode here. So the battery kind of just does work in moving these electrons in the direction that they don't want to go in. And so that's what we're talking about here. So work is done in the cell to drive a non-spontaneous reaction. It should be, we can say from the anode to the cathode. And that's really the only difference between a galvanic and electrolytic cell. So this is you're just kind of forcing things to go into the opposite direction. This is something that's kind of happening spontaneously. When we talk about non-standard cells, these get to be a little bit more interesting. But you can imagine types of situations where you might want to do this. So if you're doing like electroplating or something like that, where if you want to like take a platinum, like say you have something in your car, you want to, or like an earring or something like that, and you want to coat it in platinum or palladium or something, or nickel, let's say nickel, since that's what we have over here. You could set up a reaction like this, where you're sort of driving nickel to get plated out onto the cathode using an external power source. And that's what we talk about. That's what we'll talk about when we talk about sort of the next two learning exercises, sort of get into that a little bit. So is this how a rechargeable battery works? Yeah, more or less. The main difference between this and a rechargeable battery is that, and this is again something we'll get to in the next section in more detail. For a rechargeable battery, what you do is you let this reaction run. So on the top, you could just let this reaction run. And eventually what's going to happen here is it's going to come to equilibrium, and at equilibrium, there's going to be 0 volts in the battery. So if I just let this thing go until the reaction is finished, I'll end up with a voltage of 0 here. And then when I want to recharge it, then I go and plug it in somewhere and I drive the electrons back onto the anode, and then I can do this reaction again. The way we've drawn it out is a little bit different because all I've done is I've taken these standard conditions where we haven't even talked about concentrations yet, but and I've just flipped the battery around. So I'm still doing essentially the same thing where I'm applying external voltage, but the battery wasn't really dead in the sense that it'll run backwards. So that's sort of the weird thing. That's what makes this. That's why I took a second to kind of explain this, because I know it sounds confusing as I'm saying it. But yeah, in principle, it's the same kind of idea as a rechargeable battery. You can drive it in both directions. That's the idea here. So in the forward direction, your phone battery or your computer battery or something is acting as a galvanic cell, and you're deriving work from it that powers it, all these different kind of things on it, powers the processor, powers the screen. If you were to hook a voltmeter up to it, you would be able to see that. Once it dies, the voltage read is 0, and then I would do sort of this reaction where I'm sort of driving in the opposite way. So yeah, it is in a sense just a rechargeable battery. I'm trying to think if there's anything else to say really about these. I guess the main thing, if you go on the GChem website, I think there's a nice little chart that breaks down these things. The main thing is just that I think the main confusing thing is just the at least what I think is confusing is just that the labeling of these things is weird, right? So I've written this as the anode and the cathode. Here I'm still calling this the anode and the cathode. So what defines the anode and the cathode is the flow of the electrons. I guess it's the convention that we always write it on the left and the right, but what we're using to define it here is the flow of electrons. So even though this thing doesn't happen spontaneously in this direction because we're driving in that direction, we're still going to call this the anode over here. But you'll notice that here we're labeling this as positive and this negative. So the signs flip for the anode and the cathode, even though we're still calling them the anode and the cathode. Basically what I'm saying is in a galvanic cell, your anode is negative and your cathode is positive. In an electrolytic cell, your anode is positive and your cathode is negative. So the signs get inverted even though everything else looks the same. So these signs kind of cue you in on the fact that it's an electrolytic cell. Yeah, I think we're good to stop there. So yeah, so this is where we'll stop. Yeah, we'll worry about this other stuff. We've only got a couple more. We've got 2 more classes worth of stuff, so that's not a big deal. If you've got so if you're trying to follow along, so the LEs that we covered sort of define where let me see. The LEs sort of define where the stopping point is. I don't think we did any beyond what you should know. So if you've been following along with those, then you have an idea what will be on the exam. But if you're like looking for a quick thing of just how it's outlined, if you look at the GChem link I sent, that's the stopping point on the GChem website. So if you look at 12.1, it's oxidation numbers, redox reactions, and balancing redox reactions. There'll be a good amount of that on there because we spent some time on it. And then we'll talk about electrochemical cells. So we'll have some standard reduction potential type calculations on here. And then, yeah, voltaic versus electrolytic. Yeah, and we'll give you we'll give you a couple of hours on the exam, just like we did last time. And then, yeah, we'll kind of clean up anything that we haven't done in the last couple of days of class.
So for when you're calculating the cell, the voltage and whatnot,
Uh-huh.
can you go over again how like how you pick? Do you pick the signs on the anode and cathode basically? So like, so for this electrolytic one, we would say the it'd be like uh, whatever the reduction potential of iron is minus the reduction potential of the nitrogen or the nickel.
Let me see. So I always think about it. So the way I think, if I was trying to calculate it, the E cell here, like you're asking like down here, yeah, I guess it would be, let's see. Yeah, because I wouldn't, that's why I like this equation. So this one always holds the reduction plus the oxidation.
Yeah, in the learning modules, they said reduction minus oxidation for some reason. But they don't like.
Well, it depends on how you define these two things. So here I'm calling, this is the oxidation potential and the reduction potential. So if this is the reduction potential plus the oxidation potential. Whereas this equation oops. E cathode minus E anode, or if you did like E reduction minus E oxidation, I guess it's confusing because I guess it just depends on like how they're talking about what the potentials are, but these are both reduction potentials. So here you're taking, so like for example, let me grab these from up here. So in both of these cases, oops, these are both written as reduction potentials. So I would write that out as this. When you use these other types of equations where you're just subtracting one from the other, I don't know exactly how they're like, what the notation is that's used in the LE, but if you're keeping this consistent, then you want to do some sort of sign flip. So that's where E cathode minus E anode is the way you usually see it written out. Let's see, but you're saying that sometimes you'll see it written as E reduction minus E oxidation, which is also fine. It's another way of saying the same thing. I think the problem that you run in there, the reason I wouldn't write it out this way is because to me, this implies that you're dealing with an oxidation potential, which is, at least on the GChem website, is not how we do it. What am I trying to say here? I'm trying to say that if you're just dealing with reduction potential, so you're taking the reduction potential at the cathode and the reduction potential at the anode, then I subtract one from the other. The way I think about it is just that you're taking, you're taking the potential or the voltage associated with the reduction, and you're adding it to the potential associated with the oxidation. So here, this is the oxidation potential. So the reduction potential is whatever's listed in the table. So it's getting reduced here. Nickel is getting oxidized. So oxidation reaction. The reduction potential is whatever you see in the table, because that's how they're written out. But then for the oxidation potential, you just need to flip the sign on whatever's in the table.
Okay.
Does that make sense? I'm not sure I'm doing the best job explaining it. Yeah. So all these equations that have a negative sign in them try to account for the fact that you have to flip this reaction around, but they try to account for it in the equation. Whereas if you just always write out the reduction and the oxidation potential and add them, then you'll always get the right answer. Like you know, it doesn't. To me, it just makes more sense intuitively to do it that way. So like up here, for example, yeah, what would we end up with? I guess they both work out, let's say. So if you took the cathode potential, which is iron 2 to iron 3, that'd be 0.77 minus, well, let's see, is that true? Oh, no, so it'd be nickel, so it'd be, so if we took E cathode and subtract it from E anode, we would get negative 2.5 volts minus 0. Yeah, so you still get the right answer, so that's fine. Minus 0.77 volts. And the same would be true if you just did E reduction, the reduction in the oxidation potential. You just flip the sign on the different one. So instead of having, so E reduction, what's being reduced here is the iron 2 to, sorry, what's being reduced would be the nickel, so that would be negative 0.77 volts. And then what's being oxidized, that would just be the iron. So it will be negative as well. So they both, you end up with the same answer regardless.
Yeah. Okay.
Yep.
I like the way you explained it.
Yeah, I flip the sign, use the oxidation, and just look at the chemical reactions. That makes more sense to my chemist brain. All right. Yeah, give me a second to go and get some water real quick. My throat is kind of burning, and I'll be back, and we can hang out in office hours and work some more problems if you guys want. right, fire away if you have questions.
I think we've went over this before in office hours, but when they're talking about moving electrons, so like the total number of electrons that are moved in a redox reaction, what exactly does it mean? Question number 8 is on the homework, is one of the problems that asks about that.
Homework 9.
Homework 9, yes.
Let's see. It depends on the problem, but let me take a look before or it depends on how it's phrased, I guess. Yeah, so when they're talking about electrons transferred, which is what we'll be talking about on this exam. So there's another thing you can talk about probably where you're talking about the amount of work done and the total number of moles of electrons, which is a different problem altogether. But when you're talking about electrons that are transferred, you're talking about let's see. So like in this problem, we have they're talking about literally the number in front of the electrons in the balanced reaction, which is okay. Yeah, so this one's already balanced, so we don't have to worry about doing a whole lot of work. But yeah, if we look at this one, let's say we break it up. Let's break it up like we've been doing. So you'd have 2 electrons associated with this process because you're going from +2 to +3, and you've got 2 of each. And then for the hydrogen peroxide, you're going from -1 to -2. Of course, you've got 2 of those. So that's a 2 electron process as well. Well, they have to be the same if it's balanced. But this is the number they're talking about. So in the balanced equation, it's whatever the number of electrons associated with the sort of the reduction and oxidation is. Like an easy way to figure it out is to just find if the equation is balanced, which is an important point. If the equation is balanced, you can just take any one thing. So for example, if I recognize that the iron is being oxidized here, all I have to do is say, okay, well, it's going from +2 to +3. So that means that, let's see, it's being oxidized. That's 1 electron. But then there's a 2 out front. So I multiply that times that. So it ends up being 2 electrons. So you can look at the charge change and then multiply whatever the charge change is by the coefficient, maybe is an easy way to do it. So,
Okay.
Yeah.
Thank you.
Yeah, okay. Yeah. So here you're going +2, +3. So your charge changing by 1. And then you've got a coefficient of 2 out front. So it's 2 electron process. Let's see, does that work for this one? So here you're going from negative to -2. And so again, your charge is changing by 1. And you've got a coefficient of 2 out front. Yeah, so again, 2 electrons. I think that probably always works. But yeah, some way you have to figure that out. I think you kind of get the idea. The exam grades should be what they are. So if there's a issue with one of your exam grades, let me know. Just email me or something, and I'll take a look at them. But yeah, they should be fixed. Oh, your exam one dropped again. Let me take a look at it. Email me or something. I'll take a look at it. And I went through so much trouble with those, but it's possible I messed something up. I can look right now, actually. It might have bounced around a little bit from the just changing things, like just the way the curve thing kept getting messed up. But I don't think it should have dropped. Although Christine, I think your last name aligns with, like, there's a couple of people with your last name in the class. It's possible there might have been some like screw up in the spreadsheet. Oh, yep. All right. Yeah. Like dropped again significantly, Christine. Let me pull up the thing. Pull up my Google spreadsheet. Yeah, it's pretty dramatic. Yeah, it looks like your grade just got inverted with somebody else's. Hold on, let me change that right now. No comment on that. Okay, that is fixed now. It might take a second to go through on your end, but it's in the. I pushed that to the whatever the Canvas servers. Hopefully that's a one-off and not a bunch of people. All right. Any other electrochemistry problems?
I have a question about the grades as well. It says like for like some of the homeworks and LEs, there's like X's by them saying this assignment is dropped and will not be considered the total grade for some reason. Why is that, I guess?
Well, you said you have 5 or 6 dropped, so like your lowest of the ones get dropped.
Okay.
That's all it is. So it's not going to hurt your grade. Yeah, you just get.
Oh.
Yeah. So and then on the exams you'll get 1 dropped, but I turned that off just so it didn't falsely inflate the grade before the 4th exam. So.
Mm-hmm.
So right now your exam grade, assuming that your all your exams in are correctly, are inputted correctly, would be what your exam grade would if you just didn't take the next exam at all. But yeah, the LEs, you drop 5 or 6 of them, just whatever the lowest ones are. Same for the homework. I think we dropped 2 or 3 or something.
Okay.
Yeah. Other questions? Electrochemistry, grades, anything related to class?
So we don't need to know about work, right?
Yeah, we don't have to worry about that. We'll worry about that for the next one. Huh?
Okay.
Yeah. I think we'll come out right at the exact amount of time we need in class just to cover everything. Yeah. I don't really go through batteries because I don't know. That like standard content.
What for the like, for like practice exam, what do you think you should know?
It's a good point. The practice exam is probably not a good approximation of what the actual exam is. Let's see.
And can you explain number 9? That one was like pretty on the practice exam. That one was confusing.
In order to force a chrome finish to form the bumper of a steel car, what has to happen? Yeah, that's getting I think electrolytic cell stuff. I'll have to look at their answers. Let's see.
It says the bumper has to form the cathode
Yeah.
of an electrolytic cell. Oh, it says like it's using like a steel car, I guess. So we're supposed to assume that.
Question 9. In order to force a chrome finish, yeah, it's sort of a weirdly worded question. In order to force a chrome finish to form on the bumper of a steel car, what has to happen? So I guess you have to, steel is going to be iron. And then you're depositing, let's see, chrome. So you'd have chrome in solution, like chrome +2 or something, or +3. And then you want to force the chrome to plate out on the, let's see, so I don't know, like if you got a bumper or something, let's pretend that's your bumper. Let's just draw like a normal cathode. So let's see, so this would be, let's just assume it's just pure iron, whatever, steel has carbon and stuff in it, but, and then in solution, you'd have like platinum, and you want to plate that out on there as platinum 0. So you're trying to force electrons onto it. I don't think we really talked about how to do this. This is more related to the next, the section on doing work or something. But yeah, you'd want to somehow have some external power supply over here. Let's see. Yeah, you just want, what's their answer? Let's see. The bumper has to form the cathode electrolytic cell. Sure. I'm trying to think where your electrons come from. Yeah, I don't know. I wouldn't worry about it too much for this exam, but yeah, the bumper has to be the, let's see, so the bumper would be the cathode. Yeah, I mean, I guess you set it up like a normal, cell. So like, call this our cathode. So usually your anode is like, you know, another chunk of metal or something over here, but I think you can just replace that all together with some sort of external power supply. Is that true? I guess you have to have something where you're drawing electrons from. So I'll have to think about it. But yeah, if you had something over here, like another, I guess you need another electrode. Trying to think of like what you use as the, like you must have to have some sort of sacrificial.
Can we assume we just have like a battery or something?
Yeah. It's got to be something like that. I guess I have to think about what the exact setup is, but it's something like this. And then you have a power supply or something in the middle up here. I was trying to think of like how you would practically set something like that up. So the cathode is going to be negatively charged. It's going to be positively charged.
Are we using platinum to represent chrome or the chrome finish?
Oh yeah, sorry, it's chrome, not platinum. Whatever. Platinum's when they really made it. I guess you use, is it chromium 2 or chromium? I don't know enough about electroplating to know which one they use. Probably chromium 2, less electrons. Yeah, and then you plate that out on the cathode.
Mhm.
Let me think about it for a second. Yeah, I'm not sure practically how you set it up. I'd have to think more about that.
Okay.
Yeah, I mean, I guess in a sense what you're doing is, let me think about it. So I guess in a sense what you're doing is like, um, the electrode, like whatever the steel electrode is over there, is not actually, it's sort of not, it's not really participating in the reaction in the same way that like a platinum electrode doesn't participate in the reaction. It's just sort of there as a conduit for like the electrons and allows you to sort of plate the chromium out. So it's just, I guess it's just like a different experimental setup than we've talked about.
Mhm.
Does that make sense? Like usually what we see is like if you have iron over here, right, it's going to be oxidized or reduced and you're going to have iron in solution over here. But now we have chromium
Yeah.
in solution. So you're trying to plate chromium out. So the iron's not really doing anything. It's just kind of there. You could use some other metal conceivably and plate the chromium on it. So it's just sort of
Okay.
like, it's just serving as an electrode. And then over here, I'm not sure like what practically this is set up as, but you know, maybe you have some sort of sacrificial anode over here that you use to as a like a source for the chromium. But you might be able to just like plug it into a like an outlet or something. I don't know enough about electricity to say for sure. But yeah, that's basically it. So I guess in general, like if you wanted to sort of generalize in this question, whenever you do any kind of electroplating, um, be it on a earring or a bumper or something like that, the thing that you're plating is acting as a cathode, and you're using some sort of external power source to
Yeah.
do work on a solution. So like if you want to do gold plating, it'd be the same thing. You're going to apply some external source of power and plate the gold on there. They all kind of work the same way.
Okay, that makes sense.
This would be a bumper on the electrolytic cell.
What's that? Yeah, the whatever's being electroplated. Let's see, the thing being electroplated. Is always the cathode. On an electrolytic cell. Oops.
Do the atoms like basically form together, or like, like on like the molecular level? How does that kind of work? I guess.
Like what happens to the like at the interface between the steel and the chromium?
Mm-hmm.
Yeah, I mean, I guess you form some sort of metallic bond, and it probably is that you probably have to get into some like metallurgy stuff, but you know, you're going to form some sort of metallic bond between the two. And I imagine it depends on the types of metals that there's probably a limitation on what you can electroplate. Like you probably can't electroplate every single metal onto some other metal. I bet in some cases the plate job, like it won't form a good bond probably with the surface of the iron. What am I trying to say here? So like, you know, maybe chrome, you can form a layer on there and it's a nice, this bonded layer here or whatever, this metallic bond that you form along the interface where you have sort of iron and chromium bonds is good. And that plating job holds up really well. But there are probably metals where you have a plate that you put on top of it and it doesn't form a good bond there.
Yeah.
You know, rubs off really easily or something. So, but yeah, you form some sort of bond there.
Is it like the lattice structures kind of like come together?
Oh, like how do they stack in there?
Yeah.
Yeah, I guess so. I'm trying to think of like, I mean, they probably just stack one on top of the other. Like, what's the minima for the surface there? Yeah, it's probably something like that. Like you have one lattice structure in the bottom. Yeah, like maybe down here you've got iron atoms or something. I don't know which are bigger. I'd have to look it up. But and then up here you've got the chromium or something. Yeah, they probably deposit in a similar way. Along the surface there. So like maybe the way they nestle is different.
Mm-hmm.
because one's bigger than the other or something, or the way the metal bonds overlap is different. Yeah.
Okay.
Yeah. I'm trying to think of like a more obvious, like a common example, but it's it's not unusual to have two different materials touch up against each other, especially with metals. Yeah, don't have a lot of experience in like metal bonding, but
Oh, and if we don't have to look at number 12 on the practice exam, can you look at number 7? Because it looks like it's tying in solubility with the volt stuff.
oh yeah, no, yeah, we're not going to do that.
Okay.
Just don't even worry about that. Yeah, it's like a way to measure KSP using electrochemistry.
Will we learn that later, or?
Now we'll probably just skip that.
Okay.
I don't know who uses that. I don't. It just seemed like a side deal.
Mm-hmm.
I think it's just a way to measure. Let's see, KSP. Yeah. We'll probably skip over that altogether. I wouldn't worry about it. I'm trying to think of where you would learn that, even if you went on it. Maybe if you took a specifically an electrochemistry class. I don't know. I've never even seen that in another class. Maybe analytical chemists use it. Okay, so don't worry about that. More things like I don't know, question 4. That one's pretty easy, but yeah, question 1, obviously. Question 6 is fine. Those types of things.
Can you look at 23? Or yeah, I think it's kind of similar to the car, but
Let's see. You attended jewelry class, like this narrative they put together with it, where they teach you to perform electrolysis to electroplate gold onto a zinc change. Which of the following statements about this electrochemical cell is false? Let's see. So the cathode where the gold.
mm-hmm.
So yeah. So this is just they're just kind of asking you about an electrolytic cell. So they're saying we've got an earring, which I'm going to represent again with just a chunk of metal, and we're trying to plate out gold. Gold's what? +2. I think it's +2 or +3. I'm just assuming they use the lower oxidation state. But yeah, you've got gold in there and you're trying to plate it out onto zinc. So again, the zinc's not really reacting here. It's just kind of, whatever. It's the metal that you chose to electroplate. It could be anything. You could put gold on top of iron or nickel or something as well. There's probably some limitation to that, but you get the idea. The zinc is just kind of there. So whatever, we've got that running off to some other part of the cell, an anode, some supply of electrons. But yeah, since we know that this is the cathode, because that's what we said over here, the thing being electroplated is always the cathode. Then we can just label it like we normally would. So normally the cathode is positive, but in an electrolytic cell, it's going to be negative. So that tells you that the second answer here, let's see, cathode where the gold plate has a negative sign. So that's true, because that's true of an electrolytic cell. Electrodes are flowing from the anode through the external circuit to plate the gold at the cathode. Yeah, I mean, we know electrons are going to flow in that direction because we're putting 2 electrons onto the gold to make whatever gold 0. I don't know how you want to represent that, but the gold plate's out on there.
So the gold plating becomes like the anode, basically?
The anode is just somewhere. The anode is whatever. It's something off to the side over here that we don't care about.
Oh,
Yeah.
oh,
The gold, this cathode reaction over here is like this thing over here. The zinc is behaving as the cathode, and then we have this reduction that's taking place at the cathode.
okay.
Yeah.
For like 22, it's talking about like molarity and stuff. Do we need to know how to use that? How to use like molarity in our?
No. Yeah. So that's non-standard cells, and that specifically is a concentration cell, which are interesting. But yeah, we're definitely going to get to before the final because those things are relevant. That's how I think a lot of biological processes are powered by that. You'll have like a potential across a membrane. We have like a bunch of calcium on one side, or higher concentration of calcium on one side than the other, or something. So you get a potential across just from that. But yeah, we're not going to do that on this one. Right now, we're just looking at standard cell potentials, which we haven't really closely defined. But we just don't worry about anything with a concentration. It's like question 19, same kind of deal. That's where you're kind of generating a voltage based on like just on a concentration difference. So like, I guess it's like an entropy driven type thing. Yeah, question 13. That's a good question. I guess go through out and tell you what questions will be in there.
Do we need to know kind of like what's happening at equilibrium? Is it like the reaction just stops?
Yeah, I mean,
Why is that?
I don't know how much we talked about it, but yeah, equilibrium is like the reaction's done. That's pretty much it. Like your voltage equals 0. That's when you're at equilibrium.
Yeah. So and it's not necessarily like happening in both directions at equal rates. It's just not happening.
Oh, like it's not a dynamic equilibrium like when we look at
Yeah.
acid-base chemistry. Yeah, I guess that's true. Yeah, maybe at equilibrium. Just yeah, delta G is 0 at equilibrium. Yeah, I guess is it dynamic? I never really thought about that. I don't think so. That would imply that you have like electrons going one direction and the other direction. Yeah, I think it's probably just dead. Nothing's happening.
Okay.
Let's see, question 2. 3, 4. Okay, see a lot of this stuff is on here. Skip 7. Yeah, Q8's a good one. I don't know. We talked about electroplating bumpers and stuff, but I wouldn't focus too much on that. Let's see. Not sure what the hell they're asking question 15, but it's probably fine. So use this capable of calculating the amount of now 16 will skip. 17 we skip. 18 we skip. 19 we skip. I'm assuming 20. Yeah. obviously 24.
Should we
These
print
are-
out the tables and whatnot, or like?
I mean, that's up to you. I would just keep, if you have a large monitor, I would just put it up
Mhm.
in the corner somewhere. But yeah, you might want to print them out if it's if you can't get a good workflow with kind of switching around in your browser. I'm trying to think if I haven't looked at the. I have to look and see what we did on the exam. Whether we give you the standard reduction potentials or not, like in the problem, or link it out to some like external source. We'll definitely key you into the fact that you need a table, I think. So like, use a standard reduction potential table. We'll probably give it to you just so it's, there's not some confusion where someone goes on like Quora or somewhere and gets the wrong answer. I don't want to deal with that. But yeah, I wouldn't necessarily worry about printing anything out.
Whenever like doing the balancing reactions and basic conditions, or like acidic conditions, like I just sometimes like take a lot of shortcuts, and I don't know if it's not a good thing or not. So for like I guess like when something asks for like how many electrons,
Like how many electron transfer?
yeah, I feel like that could be solved just by looking at the equation itself.
That might be true. I have to look to see which shortcuts work and what don't. So if the equation's balanced, then definitely you can just do it that way.
Yeah.
If the equation's not balanced, you might run into some problems.
Yeah. Well, I would do it even when it's not balanced, I think.
Like just look at the charge transfer and then balance that. Just balance like part of the equation kind of idea. Is that what you're thinking?
Yeah. So like, let me try to find an example. It's not on the practice exam. It's on the homework, I think, though.
Homework 9.
It's like at number 7 and 8. Yeah, it's like how many electrons are transferred. It's like it's already balanced in this one though. So, but that one feels like it's obvious that 2 electrons.
And this one we looked at, like, let's say it wasn't balanced. Let's say they didn't get this one's not a hard one to balance. But let's say they gave us this.
Yeah.
I mean, I guess my general advice, you guys have plenty of time on the exam. My general advice would be like, in this type of environment, I wouldn't worry too much about shortcuts. If you were taking like a standardized chemistry exam, like one of those like really intense standard tests where like you got to solve things in 20, 30 seconds, like an SAT style thing, then you want to worry more about, fast ways to solve problems. But yeah, if you're looking at this, you can run into some problems. Like you can't just say, this is a 1 electron transfer process because 1 electron's going across here. You have to look at both. But you might be able to get away with just like not balancing everything. Like you could just start by balancing the charges and say, okay, well, this is this is a 2 electron process, so this has to be 2.
Yeah, because usually it's like one will be wrong, but the other one will be right. Where it's like, okay, so 2H, it's like H2O, like -1, or is that much? Like,
like the lead one, then question 9.
Let me see. Yeah, maybe that one.
Let's take a look at it.
And then I would use that to like balance the other like. But I guess if both have coefficients greater than 1, I don't know if it would work.
Yeah, I don't know. like I don't work enough with these types of things to know exactly what problems we run into, but I think that one what you just said is probably true. Like you can probably run into situations where things get weird. We can think about what that might look like. So let's see. So this is -2. So was the nitrogen being oxidized, obviously. So negative. This is +3. -6. So this is +5. Yeah. So like this would be a 2. Yeah. Okay. So this is one where we get a little weird. Okay. This one's actually not particularly weird at all. About 2 electrons. It's probably a 2 electron transfer process. Yeah. I don't know enough reactions to think of a counterexample, but that's always the concern is like, is trying to rationalize whether or not, trying to come up with a counterexample and being really confident that there is no such thing. And I don't have that in my back pocket. So I would advise against using shortcuts, I guess, in general on this exam. But yeah, I can't think of an example where you'd have to move through the problems fast, unless you're trying to go to grad school and you want to take the chemistry GRE, but I don't think that's very many people.
Okay. So for when we say like we're balancing something in a acidic or a basic solution, why is it that are we basically saying if we're in a basic solution we can only react with either water or hydroxide, and if we're in acidic we can only react with like water and hydrogen?
Yep, that's right. Yeah, it's just a way of like, it's just a restatement of kind of what we talked about in acid-base chemistry chapter, which is like you can't have this and this present in solution. Like you can't have a strong acid and a strong base because you'll form water from it. So if you're in base, it wouldn't make sense for you to react with H plus because there is no H plus around. So that's the logic, you know.
Okay.
Yeah, you can only have one or the other. In a significant amount, I should say. You can only have a significant quantity of H plus or a significant quantity of hydroxide. You can't have significant quantities of both.
Could you not is there like a situation where you could like in a basic solution produce the H protons, or like an acidic solution produce the OH? I guess that would just be like putting a base or an acid in it, or
like some really like to try to generate H plus as the reaction went. I mean, every time you generate H plus or OH minus, it's immediately going to be consumed in an acid base reaction.
Okay.
Like no matter how you work it out, you just can't really have both present.
Yeah. Okay.
I mean,
that makes sense.
Yeah. Christine, yeah, you're not going to have to worry about 12 on the exam. It's just I would just worry about these things, and I'll probably post an announcement to look at these after office hours.
Is there any other like practice work that we should do? Stuff on the GChem website, I guess, or just.
Yeah, let me take a look real quick at the.
Are there any like YouTube videos or something?
I didn't make any YouTube videos, I don't think, for balancing. Let me see. Here we go. M4. I'd have to look and see on the GChem website. I would just focus on the like things we've gone over, which is just balancing. Mostly what we've gone over is like balancing redox reactions, which encompasses things like oxidation states and electron transfer, and then electrolytic and galvanic cells, and kind of working with the cell potential. So any problems that deal with those are good. Let's see what they look at the GChem website real quick. Yeah, it kind of sucks when we get a little bit staggered in terms of the exam material. So it doesn't parse neatly. But it happens all the time. It's got wonky. That's it. Yeah, if you go on the GChem website, let's see, we've got, I'll send a link. Certainly the balancing redox reactions. Worksheets. The electrochemical cell is probably good too. Yeah. I would say those first 3 worksheets. So like this one. Is a good one. This one's a good one. That one's a good one. And then, yeah, we haven't done the Nernst equation yet, so I would skip over that. Let's see what else we got here. It's like sometimes they'll make 2 of the exact same worksheets, but with like slightly different design elements. That one's got a cleaner. Is it making a battery? Some of this worksheet is good. I don't know. Those ones are pretty good. The ones that I sent over. Trying to see if there's any other like useful ones. Yeah, these get more advanced. Yeah. Okay. No, I think those are the 3 main ones.
Okay. In terms of like, well, I guess my first question is like, can we drop the final?
We haven't talked. I haven't talked to Samoilenko right now, so I doubt we'll do that.
Mm-hmm.
But I'm not 100% on that yet. But just assume for now that.
And for preparing for the final, because can you like give us like, or not a cheat sheet, or like an idea of like what we should be studying, or like
yeah, we'll get into that more.
Concepts and equations.
We'll get into that more once we get through this exam. But I mean, I would just go back and look through my previous exams. So, you know, we're going to do probably that are really similar to those. But yeah, we'll give you some sort of idea of what the final will be. But I doubt it'll be anything. I guess we could cut some material or like weight some material more, but I doubt we'll even do that. It'll probably just be the 4 exams plus a little bit of new content from the last 2 days of class. I don't think we'll try and put any kind of surprises on there or anything. It should be hopefully just pretty one-to-one.
And so will we be having class? So our final's on Saturday, right? So will we be having class on Monday, Wednesday, and Friday next week?
I think the university's last day of class is Monday.
Oh yeah.
So yeah.
I think it's the 9th, maybe Wednesday or something.
Oh, it's the 9th of Wednesday. That would be good.
So would we have class that day? Well, it's maybe I'm wrong.
Let me look at
Not
the
the
calendar.
last class day was the 7th.
Oh, is that right? I have it on my calendar. I just need to look at it. Yeah, last day is 7th. Yeah, so Monday the 7th. So yeah, we won't have class after that. 'Cause
Yeah,
it
so-
looks like finals even start for some people on Wednesday, so definitely can't have class that day.
Okay. So just Wednesday, Friday, and Monday is our next 3 classes.
Yeah, it's crazy, but yeah, we'll have Wednesday, and then Wednesday obviously will be just kind of review, which will be. I mean, we haven't done a whole lot of material, so it's gonna be pretty. Some students, I'm sure, will have a lot of questions, but we'll just review and brush up on stuff. Then we'll have an exam. I usually give you guys off on the Friday after, but I want to make sure we have enough time to get in the stuff that we have and talk about the final. So we'll have class this Friday, and then Monday we'll have a class, and then we'll have a final exam. And so our final exam is it on Saturday, the 12th? So yeah, so we have a few days in between. So yeah, we'll probably post some reviews and updates and etc. to kind of help get prep for that. But it'll be same kind of format online on Canvas. It'll just be longer, I guess. I mean, the main difference. There shouldn't be any surprises on there.
Okay. Thank you for your time.
Yeah, all right, I'll see you guys on Wednesday.
Have a good one.
Yeah.